think it's probably problem like 24, was it? That I asked you to do for a quiz. So let me write down the term number 5 for this nice little sequence. We've been working with these sequences for a while. I hope you're getting better and better at this. So if you have a formula for the nth term that says you take a first term and you multiply it by the ratio raised to the power of n minus 1, right? One less. There's always one less. So if you asked to find term number 5, then instead of n, we have 5. Now, what do we have instead of a and r? A is 1, and that's nice. 1 is my favorite number to multiply by. So just leave it alone, in other words. And r is negative 1/3. So you put parentheses usually. Negative. Make sure it's raised entirely to the power you need. So it's 1/3. So I'm going to be raising this 1/3 to the power of 5 minus 1. Since it's a negative number, it's important to determine if it's going to be a minus sign or a plus sign in front. And looks like the answer is going to be positive because the actual power is 4. Even powers always give us positive results, so I no longer care about the minus. I even put this plus in front. You don't have to do this. And now you need to raise 3 to the power of 4. So multiply 4 factors of 3 or 2 factors of 9. So that becomes 9 squared or 81. I think lots of people got the right answer, and I made me very happy. Somebody used calculator, divided, produced points or some decimal. That's okay. A decimal is the same thing as a fraction. In this case, fraction actually is giving you precise answer because decimal needs to be rounded, but that's okay. As long as you get a close enough, that's fine with me. So these are called sequences. And what we did, we also added some of the terms of those sequences. So I didn't do problems like 41 last time, but the idea is just add first n terms. In the previous section, we were doing these procedures. So what if I try to add these terms? What will be coming out? Well, let us see what terms we're adding in here. Notice that all of them have 4 in denominators. So there'll be fractions that we add that have same denominator, which is 4. And that's great. So I don't care for denominators because we're going to be just able to factor it out. So then I need to add various powers of 2, right? So if I put this down, so keep going, n terms. So if I try to add first n terms, then the last will be power 1 less. So that'd be 2 to the power of, as they say, n minus 1, right? 2 to the power of n minus 1. Okay, so how do I possibly add these terms then? Well, notice that denominator was the same. We already noticed that, right? And then I have to add such numbers as 1 and then 2 and then 4, and then 8. So it looks like that'd be like a big number, right? And can we actually do something here about adding those terms? Well, in the section, they are discussing so-called partial sums for these terms that they like to introduce here. So they say if you take a bunch of terms and if you try to add them together, so they produce formula for the nth term. That's the one that we saw before. But how can we actually present this using a formula? And actually, I don't think they given you any formulas here. So for this section, they don't really discuss anything here. So you just can put numerators together. So you can say it's a sum. And there'll be various powers of 2. So you can say from like 1, then 2. So it looks like if I think about number 1 as a 2 to the power of what? 0, right? So my sum will start at 0 then, because that's my first term here. I'm talking about this number 1. Next will be 2 to the first, next is 2 to the second, and so forth. And I need to go all the way to n minus 1, right? And 2 has to be raised to some powers. So we don't put n, we put some other letter. Let's say k or I, so whatever letter, but not the same as n, because n is supposed to be already utilized. So I guess that's pretty much all I can say about this sum, because that's not given to us by any other formulas. But what they do, though, is they talk about something I would say pretty amazing. So here's the idea that I just tried to get across. So just put summation notation for this. Sum that ends at n. And sometimes it may go from 1 to n, and here in this exercise, I went from 0 to n minus 1. It's still n terms, but instead of starting at 1, and then 2, 3, all the way to n, I start at 0, 1 less than 1, and then I go not to n, but to 1 less. So it's, I think, interesting to consider. And this is being utilized in the following very interesting result. And this result is given to us in here. So what they do is they put it in the formula. So if I have such a sum that we have here, then what I can do is decide what a ratio is. And looks like my ratio here is 2, isn't it? Because what we do is we keep multiplying by 2, right? 2, then 2 squared, 2 cubed, and so forth. So when you have ratio equal to 2, then the sum could be treated the following way. And that's quite interesting formula for so-called partial sum, or sum of first n terms. So this sum of, well, let me write it down. So the first term, a, I'll just put it as a, so a1, and then r power of 1 less. Notice again, they don't use n, they use k minus 1, because they run from 1 to n in terms, so they don't use the same letter, they use k. That's standard. So what they do is they see that a is present in each of those terms, so they can factor it out, and then multiply it by the interesting looking fraction. 1 minus that ratio raised to the power of n divided by 1 minus that ratio. They actually show the justification of this here down below, so you can check it out. It's interesting. I guess I'm not gonna spend time checking this out. They take this sum and then they multiply it by a ratio and then they subtract, and that way they able to factor out a and then they pull out sum. So that's some algebraical standard trick. But what I'm concerned with is, since r is equal to 2 and my first term is what? It's 1, right? I say, Alex, what about quarter? Well, the quarter you could keep on the outside. It has not really participation. So my first term is 1. And the fraction will deal with ratio of 1 minus 2 to the power of n divided by 1 minus 2. So please notice that 2 to the power of n, now I should be careful because my power is not n, but 1 less, right? So what happens is I can simplify it a little bit. So I'm going to have a negative here because 1 minus 2 is negative. So we end up with a negative 1/4, right? Multiplied by this, in the parentheses, 1 minus 2 to the power of n minus 1. And of course, this negative would be distributed over, so we can actually flip the terms in the parentheses, because when you multiply by negative, the terms commute, right? So first will be 2 to the power of n minus 1, so it starts with a positive, and then you subtract 1 from it. So that'd be actual result. And of course, there is a quarter, so 4 is in. I think it's worth to take a look at this, just if you plan to go into Calculus 2 class, because that's where we work with this geometric sequences. And if not, then I think you just look at it and see that I purely utilized this formula. And that's about it. So why this is so important? And turns out there is a big reason for that. The reason is that this process enables you to precisely calculate something called geometric series. See, so far we were dealing with the sequences. So it's like starting at 1, and then 2, then 3, and then we keep going, dot, dot, dot. But series is infinite. It's always goes all the way to infinity. In other words, if you start to think about sum of the terms of your sequence, let's say if you take a sequence, you start add terms 1, 2, 3, 4, 5, etc. And say, well, it's going to be infinity because
Mister, what chapter is this?
12.
12? Okay, thank you.
We are in chapter 12. Chapter 12, and the section is 3. So section 12.3. We worked on it last time. We continue with it today. So I plan not to move away from it because the section has very interesting information for us. I think pretty new and unusual, because now they say add terms of all these sequences, and when you say, well, that's going to be infinite. Well, usually don't write the symbol infinity for the sum, but it's actually, people say approaches to, because what is infinity? It's just huge numbers, so we don't really mess with infinity. So we say it approaches to infinity. So what's infinity? Well, nobody knows actually. Something very, very, very large. I say bigger than a million. Yes. Bigger than a billion. Yes. It's just million, billion is just nothing compared to infinity. So if you start to think about numbers in terms of number line, like a 0, then you put 1, then you put 2, and etc. If you start to see how far you need to go to infinity, well, I know the largest number, it's trillion. Somebody say no, quadrillion. Somebody will say, I know a number called Google. You ever heard of that? It's one with how many zeros? It's like 100 zeros or something. Well, turns out all numbers you know is nothing compared to infinity. Infinity is just huge. So that Google, or if you have 10 to the power of billion or trillion or just whatever number you're coming up with, is nothing compared to infinity. It's somewhere around 0. See, really? So, yes. That's quite amazing. That's why it's not recommended to think about infinity. It's so huge that some people can't handle it, so they just end up at mental institutions, like some mathematicians, when they start to mess with infinity. It's just too big. And that's why I'm saying not equal, but approach it. Because what it is just not really something we can put our hands on. They trying, but they don't really go.
Yeah, that's very true, Professor. It's like it's boundless. It has no bound.
Yeah, the more people think, I'm glad that you realizing it. It's just the more people think, they just see that's like we're nowhere compared to where it is supposed to be. So we're just very close to nothing. So that's well. Anyway, so our goal is not to talk about this. In mathematics, they trying to discuss it when they learn so-called set theory. And set theory, that's area of math. They usually graduate students touch it, but again, slightly. So anyways, the message is that symbol infinity we use, but we usually end up with saying dot, 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 and that's it. So we don't really think what this is actually about. But we know that's continuous infinitely, as you wisely said, without a bound. That's another very good statement. So you cannot put bound in it. No matter what your boundary is, it goes beyond. And then you can multiply it by same as much, and you can raise to that power. So it'd be just various increases, and then whatever increases you produce turns out again nothing compared to where you can go. So anyways, so idea is that this infinity symbol is here. So that's what we're dealing with. There's so many numbers to add. And it turns out that sometimes the sum is finite. Isn't that just amazing? So you keep adding the numbers, you add infinitely many of them, and you cannot even add infinitely many. You will be adding it till the rest of your life, and your children and grandchildren and great-grandchildren inherit it and keep adding all their lives, and they still get nowhere compared to infinity. But the idea is that sums sometimes could be found if we're using geometric sequences. And that's why the geometric sequences are so remarkable. For example, if you take a sequence of numbers that deals with something like 1 over 2 to the power of n. So power will be various 2 raised to, say, first power, second power, so 2 squared is 4, third power is 8, then what, 16, 32, so keep multiplying denominators by 2. And we can actually intuitively see what the sum is going to be equal, because if I take a half, that's my first number. It's in between 0 and 1, right? And then if I decide to add a quarter to it, then a quarter will be like adding half of that distance. So if I put plus 1/4, I'll get here. And if I start to add more of these, like 1/8, which is going to be half of 1/4. But if I put it here, I'll move to the right. So I keep on increasing. Half plus quarter plus 1/8, then 1/16. So it looks like I'll be dividing what's left into 2 equal parts and moving to this next point, right? So add, and then again, and then again, and then again. Notice this procedure could be done and again and again and again, and we'll never reach 1. So it turns out that people say if you take a sum when n starts at 1 and keeps going and going, so we put infinity for that, then we're actually going to reach 1. Well, technically we'll never reach it, but the sum will be equal to 1. So this special way to avoid word infinity. So we just intuitively could see that adding this kind of fractions, dot, 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 so infinitely, roughly speaking, we get to a finite sum. And of course, if we get numbers such 1, 2, 3, 4, 5, they just keep on increasing, definitely the sum is not going to be finite. So with fractions, it works. And these fractions look like some powers of 2. And that gives us an idea that in some geometric sequences, the sums will be finite. In fact, the formula that we just used in the previous exercise, which is here, is going to help us to find those sums without doing this construction of picture. So how can I think about this? Well, turns out that if you have a ratio like 1/2, for example, because looks like in my example, I keep multiplying by 1/2 because I keep getting power of 2 in denominators. In other words, if I multiply by 1/2, so I take a half of what it was, and then a half of what it was, and again and again and again. So take a half of previous number. So actually multiplying by 1/2. So then r to the power of n, the one up here, will be 1/2 to the power of n, or I can say 1 divided by 2 to the power of n. And this is actually pretty much 0, because 2 to the power of n is very big. So if I divide 1 by some big number, we like to do this type of structure in college algebra class. We say the result is something very small. And small means 0. 1 divided by million, it's a big number. What big? Billion, trillion, divide 1 by trillion. You have a piece of candy and divide it with trillion people. So what you're gonna get? Nothing. 0, pretty much. So they say it's pretty much 0. I'm saying, no, microscopic little tiny piece, the bacteria will notice that. Yes, but it's for us, it's compared to 0. So that's the idea. When you divide by something very, very big, huge, the result is very tiny, small. And that's exactly what it says. In other words, it disappears, this. So my sum will be first term, which is a. And then you have 1, subtract that stuff that disappears. So it's just going to be 1 over 1 minus r. So just produce the formula from 1 to infinity of the infinite series. So when n approaches to infinity, so put infinity on the top, then that r to the n is 0, because it's 1 divided by b, in the case of our particular example. And then only 1 is remaining on the top, and 1 minus r on the bottom. So people just put a on the top and 1 minus r on the bottom. So in my example here, where my first term was a half, and r was also a half, look at what happens if I put this in my formula that I just produced for you. 1/2 will be and a, right? And 1 minus 1/2. So let me clear some room for that. This is interesting, right? We're trying to put our hands on infinity. Well, not really on infinity, kind of use this symbol, and that's pretty new, I think. So if I try to replace in this formula a and r with halves, so I'll be dividing 1/2 by 1 minus 1/2. Notice I'll just divide 1/2 by itself by 1/2, right? Denominator is also 1/2, right? And not surprisingly, we have the 1, and what was it? Let's see, what is that we were trying to find? Well, we were trying to find the sum of this series, if of course it's not ending at n but ending at infinity, so more terms. And remember that was 1, right? I made a little picture, just erase this. So formula enables us to find the sum of geometric series that goes 1/2, 1/4, 1/8, dot dot dot. So you just keep on adding these pieces together. And that's a formula appears here as a theorem that I try to justify to you right here. So interesting, right? And of course, the condition is r is less than 1/2 or 1/3. So it has to be less than 1. So next term will be a part of the next term of previous, because you multiply by that r, the next term you take a half of previous, so it gets smaller and then smaller and smaller, because if r is not less than 1, you will be adding bigger number and bigger number and bigger number, and of course it'll be increasing without a bound. So we'll say this is not definitely a finite sum. That's important fact that r is less than 1. And of course, signs may be positives, negatives, doesn't matter. That's why they put absolute value, because we already worked with this so-called series or actual sequences that have alternating signs, right? Plus, minus, it also works for them. Let me try to do an exercise to use this formula, and you will see if, as usual, if you have a formula, then there's nothing to think about. You just plug numbers in, and that's it. So it's our first encounter with these. In fact, I don't think we're going to encounter them again. That's why it is definitely different. But it's worth, I think, to consider. So let me try exercise number 60. I think it looks interesting because it's different. In this exercise number 60, I have to just use the formula. So when they give me terms of this series, now it is new word series, simply because we keep on adding them. Then I see that my first term of this series is 6. That's where we started. So actually it's not 6, it's 9. Okay, should be careful. 9. And what's the ratio? Would that be 1/3? Because terms have tendency to decline. So 9. So Alex, it's actually not 1/3, it's something else. It's 3 in numerator, but 4 in 3 is in denominator, but 4 is in numerator. It's 4/3. No, it's not less than 1. Let me write it. 4, because if you multiply by 4, the number will be so if I divide by 3, it'll be 3, then I take it 4 times, it's 12, right? So it's actually 4 over 3. So how did you determine it? Well, that's a ratio. So what you do is you take 12, the ratio was the previous 9. And it has to be the same if you take 16 ratio with the previous, was 12. Otherwise, it's not going to be a geometric, as they said. They use the word geometric. So just divide, and notice you can reduce and you get 4/3. Right? So it's pretty standard. I know you're not used to it, but same here. You divide by 4, the top will be get 4 and 3 in the bottom, 4/3. The ratio is 4/3. And then if you try to add terms of this, you cannot use the formula because it's greater than 1. So the sum will be, people say infinite. So they say diverges. See, they don't want to use the word infinite. They're trying to avoid it, even though it's huge, so it's infinite. People say it's divergent. That's a new word. Convergent and divergent. Something used in later classes, but I would just say it's infinite, because if it's finite for geometric sequences, a series, then we can find it. But if it's infinite, we just it's infinite. We can't find it. It's infinite. So let me do one more. I'll select one where we have ratio less than 1. Like, for example, in exercise 65, notice that you keep multiplying by -2/3, right? 65. So how do you know that the ratio is -2/3, which is an absolute value. Less than 1. So now I can use the formula that we just came up with. So how do you know it's -2/3? Well, look at how you produce your terms. You don't have to do that, but just to convince you. So first term will be 6, and then you start at 1, so power of -2/3 will be 0, isn't it? So notice that now to produce the next term, your power of -2/3 will be increased from 0 to 1. So in other words, you multiply it by -2/3. What's the next term? Well, the power here is the only thing that changes is k. So now it's going to be not 1. So start with 1. So it was 0 for the first term. Then when k was 2, it was 2 minus 1, 1. That's second term here. And then we move to the next term. So k will be 3 minus 1, which is 2. So that'd be power of -2/3 squared. So you see that you keep multiplying by minus 2/3. And what's the first term? What's my A? Well, looks like it's here. It is 6 because 0 power of minus 2/3 is 1. So it is 6. And that's it. Here's my sum. So the sum is, not gonna write that again. It's kind of hard for me to write it with this cursor, but the sum of this series and 65 is going to be, according to the formula, A on the top, 6 on the top, and 1 minus R on the bottom. And what is 1 minus R? It's not 2/3, it's negative 2/3. So whatever it is, I put it on the bottom. Negative 2/3, subtract it from 1. So that'd be actually adding 1 and 2/3. So how many thirds is that going to be? Would that be 5/3? Because first of all, this sign is going to be plus, okay, 2 minuses. It's plus, and instead of 1, I can say it's 3/3. So we have same denominator. So I add 3/3 with 2/3 to get 5 of these thirds. Let's see, what is this number? Well, do arithmetic. I advise you to utilize the denominator 3, so I multiply and the top by 3, so that complex fraction cancels. The top is only 3 and the bottom, the only 6, so I multiply by 3 my numerator and denominator, but in denominator 3 cancel. That's actually why I do this. So I get the sum, whatever it is. 6 times 3 is 18, and denominator is going to be 5. So some kind of number. Sum of this series. Notice it's infinite series, and the amazing thing is you don't have to think hard to write down those terms, they alternate and so forth. You just use the formula. The formula is here. Plug things in. So it looks like this section is again all about plugging numbers in the formula. I know it looks kind of unattractive because of formula, fractions, all that stuff. And in the case of geometric series, you will always deal with fractions to use that formula, because the key idea is that R needs to be less than 1, so it's some kind of fraction with numerator smaller than denominator, right? So it's less than 1. Absolute value, maybe even with a minus sign, like in my case here that we went over just now, R is negative. But it doesn't matter. All problems are pretty much same kind. So I'll let you maybe redo exercise 65 sometime tomorrow. Then I'll do another problem on Wednesday, and then maybe I'm going to move on from this to the next section, because I'm not planning to spend too much time on this serious story. In fact, pretty much all is set. All we needed is here. So we'll discuss a little bit more of it next time, and then we will be moving to mathematical induction. That's something very, very different. That's something that we can definitely enjoy a little bit. But I guess that's what we're going to do on Wednesday. And on Friday, some people said they live in town because of holiday, the 4th of July. So Wednesday is 3rd of July. So I guess I'll probably let you enjoy the long weekend. I'm not going to have a class on 5th of July. So that'd be the plan. So I don't give a quiz today. I'm going to stop to record. We had a quiz last time, and I was very happy with the quiz results. So thank you for making me happy. And if you did not send me the quiz yet, for whatever reason, please do so. Send me your answer. Okay. I actually worked it out in the beginning of class. Yes, you're welcome. Thank you.
Thank you, Professor.